Hi everyone, and welcome to my channel. If you're new, welcome. If you're back, welcome back. Just like every other day, we're going to start with a wildlife wild fact. And today we're talking about cheetahs. Cheetahs are the fastest land mammal, reaching speeds of 60 miles per hour in just about 3 seconds. While racing at full speed, cheetahs can cover about 21 feet with every stride. But now, cheetahs are racing towards extinction. In the year 1900, there were 100,000 cheetahs. Now, there are only about 7,000 cheetahs left in the wild. Cheetahs face threats like habitat loss, conflicts with humans, and illegal trade. When humans encroach on cheetah territory, the big cats run out of space and out of prey. This forces them to venture into farms and pasture and look at things like cows and other livestock for their food, which obviously causes issues with the humans. To learn more about cheetahs, check out the links in the description below. Alright, so today we are doing LEETCODE problem 1008 called Construct Binary Search Tree from Preorder Traversal. It is a medium level problem, but it's not too terribly difficult, so let's get to it. The problem says, given an array of integers preorder, which represents the preorder traversal of a BST, i.e. a binary search tree, construct the tree and return its root. It's guaranteed that there is always possible to find a binary search tree with the given requirements for the given test case. A binary search tree is a binary tree where for every node, any descendant of node.left has a value strictly less than node.val, and any descendant of node.right has a value strictly greater than node.val. So clearly here they're telling us we're not dealing with any duplicate values. Every value to the left of the root of a binary tree or of any node in the tree is going to be less than that node, and every node to the right of any other given node is also going to be greater than that node. We will never have a value that is equal to another node's value. A preorder traversal of a binary tree displays the value of the node first, then traverses node.left, then traverses node.right. So if you don't know about depth first search, there are 3 different types of depth first search. We have preorder traversal, in-order traversal, and post-order traversal. What's really nice about preorder traversal, which is what we have here, is that we know that we are given the root of the tree, and then the left side of that tree, and then the right side of that tree. And that really works well in concert with the fact that this is a binary search tree. So we know that when we are given the root, which is going to be the first element of our preorder array, all of the elements after it that are less than that first element go to the left of it in the tree, and all of the elements after it that are greater than that root are going to go on the right side of the tree. So we really have a lot of different factors working in our favor for this problem. Let's get right to it. The first thing I want to do is create the root of our tree. So I'm going to just say let root equal a new tree node, and we are going to put in that tree node a value that is the first element in our preorder array. So preorder at 0. Next, what I want to do is I'm going to loop over the preorder array starting at element 1, because we already have element 0 in a node. Starting at element 1, I'm going to loop through this array and insert every element into our tree as its own node. So we make our for loop, and inside our for loop, for every element, we create a node, and each node will have a value of that particular element in our preorder array. so preorder at I, and we are going to put that node into our insert function, which we haven't written yet, but I know that that insert function is going to take in the root of our tree as well as the current node. And once we have inserted every single element in this preorder array, we will return root. So now all that's left is to create our insert function. So we will obviously call it insert, and we already said it's going to take in a root and a node. So what do we do once we get this node? Well, we know with a binary search tree, if the value of a node is less than its parent, then it goes to the left of its parent. If the value of a node is greater than its parent, it will go to the right of its parent. So all we need to do is write some conditionals that do exactly that. So first we check if it goes to the left. So if node.val is less than root.val, then we have to check. If we don't have a root.left, root.left becomes our node. Otherwise, if we do have a node to the left of our given root, we have to pass this node down the left side of the tree again in order to check again. So we say insert with node.left and the current node that we are working with. Insert root.left with the current node that we are working with. Next, we have to check if the node is greater than the current root's value. So this can really just be a simple else. Normally I would do an else if, but since we know we're not working with duplicates, we only have two options. Is the node value less than our root, or is it greater than our root? So else, and we say if we don't have a root.right, then we just place our node at the root.right value. Else, if we do have a root.right, then we need to once again pass this node back through our insert function on the right side of this root. So insert, and we pass in root.right and our node. And that should do it. All we have to do is run the code. And once we get the right answer, we of course submit our code. And there you go. We got the right solution. It's a pretty good solution, if I do say so myself. If you have any questions, please feel free to put those in the comments below. If you have any suggestions for future problems, I would love to hear those if you put those in the comments below. And of course, as always, if there are any other animals you would like to hear about or want to tell me about, put that in the comments below. Don't forget to like and subscribe. And I'll see you in the next one.